So when we interpret cone penetration test results for a drain state, very simple, we use these established relationships between a normalised cone resistance QT and the initial stress in terms of some kind of state parameter. Very simple, that works for drained and undrained conditions, and no one's really thought about how it might work for partial drainage. If it's completely undrained, we can even start to recover things like undrained shear strength using the second equation there. But what happens is you transition from a drained to an undrained state. We know things like over-consolidation ratio have a big role, the initial stress state density basically, but so does the velocity of the cone. And people driven by UWA have expressed the response in terms of this non-dimensional cone velocity, capital V, which is a function of the true velocity in diameter and coefficient of consolidation. So I'm just going to outline a theoretical basis for solving this cavity expansion problem when we have this partial drainage condition. So traditionally with cavity expansion analyses, we can solve both spheres and cylinders using one set of equations, one analysis, by introducing these slightly strange stress and strain terms. The small m is 1 for a cylinder, 2 for a sphere, and away we go. The third equation there is the velocity of the material as a function of its radial tangential strains. Now the dot is a local increment, and of course locally the whole system's moving, and we have to add in the velocity component to get the material increment, which is the open circle. So this is fairly standard, nothing controversial or new here. But what we can do now is start to focus a bit on dimensionless groups. And to do that, you need to basically define or divide every variable by some scale. If it's a time variable, you need to divide it by a time scale, length scale, and so on. And the scales that I've used, T, capital S, L, capital S, subscript S, and so on, are functions of constants. So the time scale T is the small c, which is your coefficient of consolidation, divided by the velocity of the expanding cavity squared. I'm solving the problem when the velocity is constant. And now the stress scale S is simply taken to be the constrained modulus of the soil as well, which is a constant for a given set of initial conditions. So then you can convert all the other variables, the real time, the real length, the real radius, the real velocity, to a dimensionless term by dividing by one of those scales. And we also then go a step further and express all the variables when dimensionless in terms of a dimensionless radial distance from the cavity wall, which is capital eta, it looks a bit like a H, and you'll see all the differential equations expressed in terms of that particular variable. So the governing equations, most of them are fairly standard. The first one's stress equilibrium, stress-strain relations to the constitutive model. I've just adopted sort of very standard elastic plastic model formulations here. You can put in any constitutive model that has that structure. Continuity just relates to your increments of strain and specific volume. But there's a new continuity equation which we have to introduce, which relates to the way that pore pressures build up as a function of the volumetric strain rate, and that's in the red box there. The small k is your permeability, the m is your unit weight, and so on. So that's really the new equation inside the governing equations. Everything else is pretty standard. Now, so there's the new equation again, but what was really key here was to realise that every variable is now a function of distance from the cavity as well as time since the expansion began. So we've got, two multivariable calculus, very difficult to solve semi-analytically, so we can trick it or come up with a solution by setting one of the variables constant, and that happens to be this dimensionless time. So rather than expressing all the equations